Hello, beautiful people. I am taking the day off to grade your IAs, so let's have some fun in a screencast. The last we talked, we were calculating the force exerted upon an object by another moving object. And so, that's what we can see here. This is what we did on Thursday. We use these formulas, the scalar product and the vector product, divided by the magnitude of the second vector, to find the component of one vector acting in the direction of another. And so these formulas up top gave us a nice direct way of calculating that. But please remember that for these types of problems, with exercises 12A and B, you really need to make a diagram and understand what we are talking about. All right, now there are a few homework answers in here. For example, exercise 12A with the sled dogs. Please review those. They're in yesterday's slides as well as today's. Exercise 12B, number 1, problem 2 as well. What I wanted to talk about today, though, was motion in 2 dimensions. All right? So this is a formula that I believe is in your formula packet, but it's what we already know. All right? So if displacement we call r of t, I know we called it previously s of t, but if we're talking about a vector, and we call displacement r of t, then as a column vector, we can write it as f sub 1 times t, f sub 2 times t, t being time. Remember, t is time. And so f sub 1 is going to be the x component, f sub 2 would be the y component. So where is this vector? How much has it been displaced on the coordinate plane? If we have that vector, we can find the velocity vector simply by taking the derivative of the displacement vector, and we could find the acceleration vector simply by taking the derivative of the velocity vector. Ha! We can also work backwards by integrating. So let's take a look at a couple of problems that use this. Whoops, sorry, I didn't mean to do that. All right, let's look at this problem right here. All right, a particle has a velocity v of t, where v equals 4t minus 6i minus 3tj. Find the speed of the particle when t equals 3. All right, we've got to understand a few things here. Okay, first of all, I like to write my vectors in column form, so I'm just going to do that. v of t equals 4t minus 6. And negative, what is that? Negative 3t. Yeah, negative 3t. All right, so this is my, these are my I and j, my x and y components. We're going to find the speed of the particle when t equals 3. So, speed is the magnitude of velocity. All right, so let's find when t equals 3, let's find the velocity at time t equals 3. Well, that's going to be 4 times 3 minus 6, negative 3 times 3. All right, and so this is going to give us 6, negative 9, right, as the velocity. But speed is the magnitude of that. So speed is going to be the magnitude of this column vector, which is going to be this. All right, that's the square root of 117, which is approximately 10.8. All right, so 10.8, what are our units here? Speed. Okay, it doesn't say any units. All right, fine. Okay, part B. Here, part B. Find the time at which the direction of movement of the particle is parallel to J. Now this simply means that, remember, remember, j is our y component. Let me just jot that down here. This is our x component, which is I. Second number is our, second component is our y component, which is j. So if the particle is parallel to j, that means it is not moving at all in the I direction or in the x direction. So basically, we have to find t when I equals 0. When the I component equals 0. All right, and so simply what we're going to do is set our I component equal to 0, and we find that t equals, what's that, 3/2. Ta-da. Now, part C, show that the acceleration of the particle is constant. All right, we're going to have to do some calculations here. And we are looking at acceleration now. Since we know that acceleration is the derivative of the velocity vector, well then, let's take the derivative of this velocity vector. All right, so let's find dv dt with respect to time, of course. The derivative of the velocity vector is going to be the derivative of this which is what? Well, what's the derivative of 4t minus 6? It's 4. What's the derivative of negative 3t? It's negative 3. This is constant. Our acceleration is constant. There's no variable, so it is not variable. Let me clean this up a bit. Hang on. All right. So part D is the fun one here. Given that the displacement of the particle when t equals 0 is 4I, find an expression for its displacement at time t. All right, an expression. We need to find like a formula or an equation. Well, in this case, it'll be the vector expression. So, remember, how are displacement and velocity related? We've been given velocity, all right? We need to find displacement. And when we're dealing with vectors, or displacement vectors are, we know that the displacement vector is the integral of the velocity vector, as displacement is integral of velocity. So let's integrate the velocity vector. All right, so this is going to be the integral of 4t minus 6 negative 3t dt. All right, and so we can integrate these two separately. All right, now what is the integral of 4t minus 6? That's going to be, well, let's use the power rule. Increase the power of t by 1, so that's 4t squared, but divided by that same exponent, so that gives us 2t squared. 2t squared minus 6t plus some constant, all right? And then the integral of negative 3t is negative 3t squared over 2. Don't forget your plus c. And so, how can we find c? Well, t equals 0. When t equals 0, the displacement is 4I. Right, so we know that r of 0 equals 4I. So 4I is 4 and 0 in the j direction. All right, meaning that if we were to plug in 0 for t, all right, 0 here, here, and here, what we should get is 4 in the in our x component and 0 in our y component, meaning that the plus c up top is 4 and the plus c at the bottom is 0. All right, so r of t, the expression for the displacement, is going to be 2t squared minus 6t plus 4 negative 3t squared plus 0. And And that is that example problem, using derivatives and or integrals to talk about variable velocity. Now, in exercise 12C, I want you to try problem 3 right now. Pause the video, pause the video, and then check your work. Please know that the work is posted in the slides, and again, it's right here in the video. Ask me any questions about this problem, which I think is fairly self-explanatory, but ask me any questions on Monday. The problem I want to go over with you that's a little bit harder is this problem from exercise 12D. We're talking about gravity now. Okay, so in these problems, in all of exercise 12D, it says, take G stands for gravity, equals 9.81 meters per second squared. I want you to see that squared. First of all, that indicates a second derivative, all right? Meters per second squared. Now, gravity, you need to understand, is a downward force, okay? And for all these problems, you should ignore external forces such as wind, air resistance, etc. All right? So problem 1 here, an object is projected with an initial velocity with this column vector, 5.2 meters per second. Notice the units here. This is velocity, meters per second. And notice the difference. Gravity is meters per second squared. That is a second derivative. All right? So this many meters per second from a point 1.5 meters above ground level. Write down the acceleration vector for the particle while in flight. Well, we know that acceleration is the derivative of velocity. And so if we were to take, acceleration equals the derivative of velocity with respect to time. And so if we were to take the derivative of this velocity vector, we would get 0, 0. But you have to keep in mind that there is still a downward force pulling on this object. All right, and so therefore, the acceleration is going to be 0, not 0, 0, but 0, negative 9.81. Because this right here, this negative 9.81 is the force, gravity. All right, so this is the acceleration vector. 0, negative 9.81 meters per second squared. Oops, that's an S. Now, based on this, part B, find an expression for the velocity and the displacement. Okay, so an expression means we need to come up with a formula, meaning some sort of derivative, integral, something like that, with the variable t for time. All right, so let me do part B up here. Oops, I wanted to do that in blue. All right, so if we know that acceleration is negative 9.81, well, what can we do? We can actually integrate the acceleration vector. It's the integral of the acceleration vector with respect to time, and we actually know the initial velocity right there. So this is going to be the integral of 0, negative 9.81, 0, negative 9.81, dt, all right? And since we already know the initial conditions, initial is when t equals 0, we know our c values, all right? So here the velocity is going to be 0t. What do I have here? 0t, yeah. So this is going to be, what do I have? 0t plus c, all right? So our c and negative 9.81 t plus the other c. Remember, we know our c values because v of 0, where am I going to write this? V of 0 equals 5.2. All right, and so therefore, these are our c values. So when I substitute 0 in for t here, I know that I'm going to get those two c values. So v of t, my expression is 5, negative 9.81, t plus 2.